This video introduces Chapter 4, which is on oxidation reduction reactions and the role they play in the natural environment. It's been brought up in previous discussions in this course, the question, what is life? Now, I would argue in this context that life is by nature a redox reaction. And if you think about a living organism and what it takes to stay alive, not go to equilibrium. We know that once we die, that is when our delta G, our free energy, equals zero. But it's redox reactions through metabolism and the pumping of electrons and protons across membranes that keeps us alive and keeps us out of equilibrium. So these redox reactions in the biosphere and hydrosphere, they have constraints with respect to stoichiometry and essentially the Redfield ratio. They cannot just happen at their own will. So it is life that drives a lot of these reactions, and they play a big role in geochemical cycles. And for the main reaction that drives all redox reactions in the biosphere, it is photosynthesis that initiates this process. So let's look at photosynthesis again in the context of oxidation reduction reactions. First of all, we should note that photosynthesis is a thermodynamically unfavorable reaction. It just doesn't happen on its own. We need sun. We need an external energy source to drive this reaction. And we can also see from the delta G, because delta G is positive, we know that this reaction is non-spontaneous. It cannot happen on its own. Also, typically, we would write the equation for photosynthesis like this, where CO2 and water goes to biomass and oxygen. But in fact, the reaction is made up of two half reactions. We call these half reactions, where we're actually getting the transfer of electrons, and the electrons are coming from water, and then those electrons are being accepted by CO2 to make the biomass. And so in this first reaction here, where CO2 is accepting the electrons, we would call this reduction. So we are getting reduction in that half reaction. And for water, as it loses electrons, this is going to be oxidation. So if we add these two reactions, we notice that the electrons cancel out and they do not show up in our final answer. And these products of photosynthesis, these are the things that drive other redox reactions, continue to react with other elements. So we have the biomass, we have the organic matter, which after this process is over, is a molecule that has lots of electrons. We would say that this carbon here in biomass is reduced carbon. It contains a lot of electrons. That is why organisms like us seek out food. Why do we seek out food? It contains a lot of electrons. It contains other nutrients. It contains elements that help us fulfill our stoichiometry. But food contains electrons, and we run on electrons. Also, we have oxygen. And this oxygen that's been produced, it's actually void of electrons. It would like to have more. Of course, oxygen gas has electrons, but the oxygen atoms within oxygen gas would like more. So it actually behaves like an electron drain. And so we need oxygens because we respire. We need oxygen because if we eat that food, if we eat that organic matter, we need somewhere for those electrons to go. And so combined with biomass and oxygen gas, it gives a pathway for those electrons to be transferred and for our cells to use the work from the electrons. And so again, photosynthesis fuels a lot of other redox reactions on the surface of the Earth. And this would be redox reactions with nitrogen, sulfur, iron, and other elements. And so let's review some of the general terminology for oxidation reduction reactions. So first, definition of oxidation and reduction. So oxidation is when an atom or molecule loses electrons during a chemical reaction. And reduction is when atoms gain electrons during a chemical reaction. One easy way to remember that lost electrons in oxidation and gain electrons in reduction is Leo the lion goes grr. There are other ones as well. So let's take a simple reaction. This is actually a spontaneous reaction where if you put a piece of zinc metal in a solution of copper 2 plus, you have water, but you have copper ion in solution, the zinc would spontaneously oxidize, because we see here that the zinc goes from metal, which has a charge of 0, to a charge of 2 plus. It lost 2 electrons. And the copper will actually blacken the piece of zinc metal because it becomes reduced. At the surface of the zinc metal, copper 2 plus would gain 2 electrons to make copper metal. So it actually coats the zinc metal. And so that is reduction, gaining of electrons. We could write this in terms of half reactions, showing the reduction of copper 2 plus and showing the oxidation of the zinc metal. So as we go forward, we can actually assign numbers, voltages, to these reactions. These voltages help us understand, as written, either as oxidation or reduction, whether or not the process, the loss or gain of electrons, is favorable. And we will discuss that in a later slide. What we have here is a new equation that connects the free energy to the voltage. Voltage is like work. This is electrical work. And we're going to find that if, say, we have a negative delta G, at this point, we should know from chapter 2 that a negative delta G is spontaneous. It will happen. Therefore, if a negative delta G is spontaneous, then a positive voltage is spontaneous and will happen on its own. So we see for both of these half reactions, both of them are encouraging spontaneity. And when we put them together, or in the terminology that we'll use in this chapter, if we couple them, then this reaction will become spontaneous. This overall reaction has a positive sign. This reaction will happen on its own. So this is just terminology. We'll continue talking through a lot of these ideas. So let's look at a few other terms that are commonly used in electrochemistry, oxidation reduction. So we have defined oxidation as losing electrons, reduction as gaining electrons, but also these reactions and the species involved are commonly referred to as reducing agents or oxidizing agents. And this can be confusing if you're not paying attention. So reducing agents, they are species that readily donate electrons to another species. So that means they reduce something else. That other species became reduced. However, that means that the reducing agent became oxidized itself because it lost electrons. It gave its electrons away. On the other side of the reaction, we have the oxidizing agent. The oxidizing agent, that is a species that readily accepts electrons. And the oxidizing agent itself became reduced. So think about that. In a reaction where it is spontaneous and actually happens, you will have on the reactant side an oxidizing agent and a reducing agent. You will have something that becomes oxidized and reduced. You must have electrons transferred in order to have a redox reaction. So let's look at the numbers. So in the next slide, I'll show you table 4.2 out of our text, and we will expand this smaller subset of standard electrode potentials that I have here. So when we look at the tables, just note all the reactions by convention are always written as reductions. That is just to keep the situation simplified. We can always flip an equation, turn it around, and if we turn around and flip a reduction reaction, we have now written an oxidation reaction. So that's the only difference between a reduction and oxidation reaction, is what side the electrons are on. And so in all of these cases, what I have written here, the electrons are written as reactants, and we have a species that is accepting those electrons. They're gaining electrons. And all of these species over here are reduced as they accepted those electrons. If we flip these reactions and wrote them with these products over here as reactants and the electrons as products, we would have oxidation. So what we have in these tables are different values, and they are all relative to what we call standard hydrogen electrode, which is where we have hydrogen ion plus 2 electrons going to hydrogen gas. By convention, we have called that R0. It is arbitrary, but in order to assign numbers to these reactions, I needed to call some reaction 0, and now everything else is based upon that point. And so we have that reaction as 0, and then everything else that's more negative, and everything else that's more positive we can put into tables. And so if the voltage is negative, that is unfavorable as written. We could see that if we flip the reaction, here, it would be favorable, because when you flip the equation, you change the sign. So this reaction here would have a positive 3.045. And we know that positive signs are spontaneous. Positive voltages are spontaneous. And so what occurs in nature is two of these reactions become coupled. And if by adding the two reactions, the overall reaction has a positive voltage, then you have a spontaneous reaction. It will happen on its own. And remember that these voltages are linked to delta G. And again, delta G, if it's negative, will also be spontaneous. The last point here is when we look at these values in the tables, and when we see something negative, it does not want to become reduced. Because again, everything written in the tables is as a reduction. It does not want to become reduced, but that means it does want to become oxidized. It does want to become oxidized. It does want to give its electrons away. So that means here that lithium metal is a very good reducing agent, because written in this direction where it's favorable, we see that it really wants to donate electrons. And a value of 3 volts is huge. That is a huge voltage. That is why they make batteries in your computer and phone with lithium, because it gives you a good charge and a high voltage. On the other end, we have here gold 3 plus, accepting 3 electrons, going to gold solid. Written as a reduction, it has a positive value. It is spontaneous in this direction. So we could say that gold 3 plus is a very good oxidizing agent. It is a very good oxidizing agent. It wants to take electrons from something else because it would like to form gold solid. So we need to think in terms of oxidizing agent, reducing agent, and just general spontaneity in terms of looking at the signs for a given half reaction or overall reaction. And so last, here is table 4.2. Here's lithium. It's at the top of the table. So it's the best reducing agent. And you might need time to think about reducing agent, oxidation, reduction. And down here, I have gold 3 plus, which is positive, and at least on this table, it is the best oxidizing agent. So this stuff does not come quickly if it's the first time you've heard of these terms. So on this table, they're usually written in concession of increasing negative and increasing positive voltage. And again, we can start using this table to couple different half reactions, one written as oxidation, one written as a reduction, and start to figure out whether something is spontaneous by looking at the sign on the overall reaction.